Look, I call the deseasonalized series data D, and basically it's obtained by subtracting from the data the repetition of the seasonal mean for a length which is equal to the length of the data, because the seasonal mean is 365 long. In order to be able to subtract two vectors, I have to make them the same length, and therefore I repeated the seasonal mean to get to a length which is the same of the original series. And then everything is closed, and there is a division by the repetition of the standard deviation, of the seasonal standard deviation. This is how the deseasonalization was performed. Please note that we didn't smooth the data, which is not really the best thing to do, but in any case. Okay, so now let's make a comparison between the autocorrelation function. I'm not sure if there is the plot first of all. So let's just make a plot first. And here is the plot. So you see that now the series look different and you don't see the cycles anymore. Good. And let's look at the autocorrelation function. First of all, ACF of data, and like that max equal, well, we can do 730. So this is the autocorrelation of the original data. You see the usual periodicity. This is what we were expecting. And now let's look at the autocorrelation of the deseasonalized data. You see that there is basically no more periodicity. You can still see some periodicity, but basically we are quite satisfied. Why can you still see some periodicity? Because these deseasonalization procedures are approximate procedures. You are not completely removing the seasonality. If you remove the seasonality in the mean and standard deviation, there might be some behaviors that remain seasonal, like also the memory. The memory of the past will be seasonal, because usually rivers remember they passed more in autumn here than in the summer, because rainfall in autumn is more persistent. And therefore, some behaviors may remain seasonal. So in the autocorrelation function, you may still see some seasonality. And therefore, you may conclude that your deseasonalization was not successful. But of course, we have some tolerance, and in this case, I would say that basically it's fine. You see the blue bands and are your term of comparison. Okay, so now we are ready to estimate our autoregressive model. We could also make a plot of the density. Which looks not bad. It's symmetric, maybe it's not really Gaussian, but it's not bad. It's not long-tailed, so So now let's estimate the progressive model, and then we make a short break. First of all, we estimate an AR1, and therefore with this instruction I put a 0 at the beginning of the series. Why should I put a 0? Just because, if you remember, we said that it's a problem to start from the first time interval with an AR1 because you don't have the previous observation. So either you start from the second time interval or you add a 0 at the beginning. I decided to add a 0. And by adding a 0, basically, sorry. No, okay, I go back to my description. Because I'm not using now the R routine to estimate the AR1 model, which basically would do this operation by itself. I just want to estimate the AR1 model by setting up a program myself. And therefore I need to express each observation as the product of phi 1 times the previous one. And therefore I am creating a series which is just shifted by one position with respect to the seasonalized data. Because I want to get two vectors, one shifted one position with respect to the other, in order to be able to multiply these two vectors and obtain the result. Basically, I think you understood, no? Anyway, I have a vector of observations where each small bar is a number, and then, of course, you remember that the model is xt equal phi 1, xt minus 1, sorry, xt minus 1 plus epsilon, and what I want to do in order to estimate phi 1 is, as you may remember, to minimize the magnitude of epsilon, so I have to compute epsilon for various values of phi 1. So the easiest way is to compute this relationship for, at the same time, for all the data by multiplying two vectors. And therefore I get, these are the data, I get the shifted data, which are 1, 0, and then the data. And then I have one more, which I skip. So you see that if you write the indexes here, you have 1, 2, 3, the time indexes. 1, 2, 3. So now if you multiply these two vectors, you obtain the product of x2 times x1, which is this one. And therefore you can compute the product just by multiplying two vectors. So I need a shifted vector. Good. Now, let me go back to the code. Let's define phi 1. We need to define the parameter with just a guess value, 4.1. And then look at what I'm doing. I am defining a function which gives back the sum of squared residuals. Residual is like a synonym of error. Okay. If you don't mind, I make a break, and in 10 minutes we will start again from here.